So we are dealing with the third problem in this series, and we are dealing with problem 3.21. The problem is stating a ball of radius r is uniformly charged with a volume density rho. Find the flux of the electric field strength vector across the ball's cross section formed by the plane located at a distance r0 which is less than r from the center of the ball. So this is what the problem is stating. Let us understand this thing from diagrammatic point of view. So diagrammatically, this is how we are supposed to understand this problem. That over here we have a sphere of radius r, and it is having a volume charge density rho. Now the flux over here is asked due to the electric field, and the section which is said to be the plane is this at a distance r0, and the plane is AC through which the flux is to be calculated. So this is what exactly the problem is asking us to do. Now in order to start approaching this problem, we first of all apply Gauss law for the problem, and we apply Gauss law over this region. So we consider a sphere of radius r, which we consider this as radius r, and for this radius r we apply Gauss law to calculate electric field at this point, which we are referring as point P. So in order to apply Gauss law, we say rho equals charge enclosed upon volume. So volume over here is 4 by 3 pi r cube. So we can say that charge enclosed is equal to 4 by 3 pi rho r cube. And therefore if we apply Gauss law, we can say E dot A is equal to Q enclosed divided by epsilon naught, and we get E into 4 pi r square is equal to 4 by 3 pi rho r cube divided by epsilon naught, and we get E at this point P as rho r by 3 epsilon naught. It is also the classroom result for electric field at a point inside a sphere. So we have obtained this result first of all. Now the problem is asking us to calculate electric flux through this plane, which is at a distance r0 from the center. So to understand this, let us come over here and understand the situation like this. So we are talking about here at this point, which is at a distance r. So we have calculated the electric field at this point, and the electric field is calculated as E vector directed away at a distance r. So this E vector is going to have two components. One component will be E cos theta, and the another component will be E sin theta. So E sin theta is not going to contribute through any electric flux through this surface ABC, which we are naming as ABC at a distance r0. The electric flux contribution is solely coming due to the electric flux caused by E cos theta. And E over here we have already calculated as rho r by 3 epsilon naught. So E at this point P is calculated as rho r by 3 epsilon naught, and the electric flux contribution will be taking place only because of E cos theta, as E sin theta is perpendicular to the area vector which this surface will hold. So therefore if I calculate electric flux d phi, so d phi is going to be due to E cos theta multiply by ds. So E is equal to rho r by 3 epsilon naught cos theta multiply by ds. This is electric flux d phi, and over here we say r cos theta. So if I look at r cos theta term, So if we take any point over here on this plane as point P, so this r cos theta term is going to give us this r0 value, which is mentioned in the problem, where the problem is asking us to calculate electric flux formed by a plane at a distance r0 less than r. So therefore we can say that electric flux d phi can be written as rho r0 by 3 epsilon naught, and we have integration of ds. So we need to integrate this surface area to calculate the value of integration ds. So this is the area that we need to calculate. For this we have this distance mentioned as r0 and the radius is capital R. So over here we can say that if this radius is capital R and this distance is r0, so we can easily calculate radius for this shaded part as r square minus r0 square is square root. And if we put the area integration of ds as s as pi r square minus r0 square, then we will get the final answer as phi net through this surface is equal to rho pi r0 r square minus r0 square by 3 epsilon naught. So this is the final answer for the problem which we have discussed, problem number 3.21, where the first important aspect is to understand what exactly the plane which the problem is referring to. So this is the plane which the problem is referring to. The next thing that we do is we calculate the value of electric field at the point P, and then we calculate electric flux due to the electric field vector. So E vector is E, which is making an angle theta like this. So we break the component of E. Now E sin theta is not contributing for any electric flux, and then we calculate electric flux due to E cos theta component, where R cos theta at any point on the plane can be written as R0. So this is the final answer that we have for this particular problem.